Hey PCalc, I've got a little addendum video that's just attached to kind of what we were doing with absolute max and min. What do we do if the boundaries, quote unquote, are unbounded? So check out number 17 with me on the Anton problem set. You got f of x is equal to 4x cubed minus 3x to the 4 power. I think that's what it is. Yeah, and we're saying it's unbounded. What is the absolute max and absolute min when there are absolutely no boundaries at all? Well, we can first, we can try for a relative max or min value, right? The critical numbers are still potential candidates. So when we take the derivative, you get 12x squared minus 12x cubed. I think we worked with this when we zoomed yesterday. Yeah. So 0 equals that. The two solutions would be 0 and 1. It was very similar to this. So x equals 0, x equals 1. Those are both potential candidates for an absolute max or absolute min value. So we're going to test x equals 0, test x equals 1, and then I'll talk about what the heck we're supposed to do with these endpoints. So when you plug those into the original, you get 0. When you plug 1 in, you get 1. Now here's the deal. I can't actually plug in negative infinity, but I can compute the limit as x approaches negative infinity. See what I'm doing here is I'm doing the next best thing. I'm saying can't plug x in, but if x were to approach negative infinity, then I can calculate it up here. So what would the behavior of a polynomial be if you plugged in negative infinity to this part versus plugging it into this part? Now there was a polynomial rule when we did infinite limits where it stated whatever the behavior of the leading power is going to be the behavior of the total polynomial when you go to negative infinity and positive infinity. You got to test them both separately, though. So what we're saying is the negative 3x to the 4, that bears pretty much all the weight of what this function's y values will be at both positive and negative infinity. So when you plug in negative infinity, you're taking that value of x to the 4th power. What does taking a negative number to an even power result in? Positive. So whatever you plug in here, it's going to be a positive number. It's a huge positive number, and you're multiplying it by negative 3. That's making it a really, really, really negative number. It's a big negative digit. So, yeah, it equals negative infinity, which instantaneously means we don't have an absolute min, because it keeps going down forever. Do the same thing with positive infinity, and you'll notice, the exact same thing's happening. But plug in positive infinity, you get a really huge positive number times negative 3. So that's also negative infinity. So here's how we conclude. If I see negative infinity in the right-hand column here, there is no absolute minimum. And the absolute max, it's 1. And I hope this makes sense if you go to Desmos and graph this thing. I'm hoping you kind of remember from pre-calc how to graph this thing. If the leading power is even and the leading coefficient is negative, then that means it's going to do something like this. All right. In this case, it's probably going to have a little extra bump to it. Probably something like that, or the reverse of it, which makes a whole lot of sense. It's like, oh, okay. That's clearly the peak, and it never has a valley if it goes from negative infinity to infinity. Okay, there's your answer. Let's try 21 now. 21's a wee bit different. We still have a polynomial. It's still going from negative infinity to infinity. But there do seem to be some strikingly different characteristics. For instance, the leading power is odd, not even. That'll probably change some things. So, I don't know, maybe right off the bat. No. We'll find the Crumbers first. You get 3x squared minus 3 plus 0. You can divide both sides of the derivative by 3, just to make things simpler on us computationally. You get x squared minus 1. Ooh, add 1 to both sides. Don't forget your plus or minus. These are ones to consider. Consider x equals negative 1. Consider x equals positive 1. And then we consider negative infinity and positive infinity. So plug in negative 1. You get negative 1 plus 3, 2 minus 2, 0. 1 minus 3, negative 2 minus 2, negative 4. All right, negative infinity. We've got a polynomial, which means you can ignore everything after the leading power. Okay, so, whoa, I just ignored you guys. Oh, that wasn't as cool as I thought it would be. Yeah, whatever. So x cubed, what happens when you plug in negative infinity? Well, the odd power forces everything to negative infinity. So there's no absolute min. How about positive infinity? It's a positive number. There's no absolute max. There's no absolute max. There's no absolute min. What do? We write there's no absolute max or min. Which is sort of like, oh, duh, it was one of these deals. Of course there's no absolute max or min. See, this is where having that pre-calc graphing sense chapter firmly saturated into your brain makes analysis so much simpler. Okay, last one I wanted to show you guys, or maybe that's it. Maybe that's good. Yes. Maybe I'll talk about a different one through Zoom. All right, things are getting awkward here. I'm just going to stop the video.